Now we come to the sessions 15, some functions of a power series. Now we already know in the previous session in 14, what's the convergence within a unit circle is a convergence, outside a circle is a divergence in the power series form. Now come to the some functions of a power series. If a f of z equal to summation n run from 0 to infinity a n z n, where then f of z is called a sum of functions of a power series. So sum of functions of a power series. So we come to the in the theorem form. The theorem say the power series summation a n z power n, either first one is convergence for every z, is convergence for every z. Second is convergence only for z equal to 0. Third one, the convergence for some values of z. See, in the previous session we draw values convergence depend on values of r. Value if a unit r equal to 0 and the unit and infinite, it's a finite and infinite form. The same way this theorem depend on z. It's a convergence for every values of z. It's a convergence only for z. Convergence for some values of z. So it is sufficient to provide some example in each cases. Consider a power series summation zn divided by n factorial. So see, by using a comparison test, comparing this with summation un of z, so we can find out the ratio formula un plus 1 divided by un is equal to replace n by n plus 1. We get z power n plus 1 divided by n plus 1 factorial whole divided by z power n divided by n factorial. Again, a numerator go to denominator, we get z power n plus 1 divided by n plus 1 factorial into z power n divided by n factorial. So one term get cancels. So what we get? So after we get z power n, so one term, so n factorial, we can n plus 1 factorial, we can write n plus 1 into n factorial. Here n factorial get cancels, left n plus 1. Again z power n plus 1, we can write z power n into z divided by z power n. Again z power n get cancelled, simply we get z divided by n plus 1. So if we take absolute value, limit n tends to infinity, absolute values of un plus 1 divided by un is equal to limit n tends to infinity 1 divided by n plus 1 absolute values of z. So if we limit n tends to infinity, this value should be as 0. So suddenly 0 less than 1. Hence the power series zn divided by n factor is convergence for every values of z. Now consider for power series summation zn into n factorial. So this can be written as summation un, say. So limit n tends to infinity, absolute values of un is equal to limit n tends to infinity n factorial into z power n. So this value should be a 0 if z equal to 0, infinity if z not equal to 0. If 0 is convergence, if not 0 is not a convergence, simply say a divergence. So summation un, that is summation n factorial z power n, is convergence if z equal to 0 and divergence if z not equal to 0. This is the second case. For if come to the third case, the power series summation zn is convergence if mod z less than 1, is not convergence if mod z greater than or equal to 1. So the power series summation z power n is convergence if mod z less than 1, is not convergence if mod z greater than or equal to 1. So we prove one more theorem in the power series in a convergence form. If the power series summation a n z power n is convergence for particular values of z naught of z, then it is convergence absolutely for every values of z for which mod z less than mod z naught. In another way, So in this you want to prove this. Suppose the power series summation an z power n is convergence for z equal to z naught, so that the power series summation an z power n is convergent. Consequently, if you take a limit n tends to infinity, an z power n equal to 0. Our aim to show that summation an z power n is convergence for every z for which mod z less than mod z naught. Convergence for which mod z less than mod z naught. You call this equation 1. For there exists a positive real number. You say there exists positive number m. This should be a greater than 0 such that mod an z naught power n less than or equal to m for all values of n. That is, we say mod an z power n less than or equal to m divided by mod z naught whole power n into mod zn. That is, this implies m is equal to m into z by z naught whole power n. So that is, we can say mod an z power n less than or equal to m times of z divided by z naught whole power n. But we compare the geometric series. But the geometric series say summation zn divided by zn whole power convergence for every values of z such that mod z minus z naught less than mod z minus z naught less than 1. That is mod z minus z mod z naught, which gives, by comparing tests, the power series summation an z power n is convergence for every z such that mod z minus z naught. Consequently, the power series an z power n is absolutely convergence for all z such that mod z minus less than mod z naught. Mod z less than mod z naught. Now, here, see, you are using this theorem. It says every power series where is something it says is bounded form. So less than or equal to some positive real number, we say the same. So conversion by using comparison test, mod z minus z naught less than 1, say mod z minus mod z naught, which gives, that is comparison test. This is say mod z minus mod z naught. So we come to the one more theorems. We say if we take a power series, if we differentiate with respect to z form, that is, we call with one function, we call it another function. We say, suppose to show that the power series to show that the power series summation an z power n minus 1 is obtained by differentiating the power series, summation an z power n as same radius of convergence as the original given series summation an z power n, as the given original series summation an z power n. If this power series is differentiated, we get n z power n minus 1. So let I call that number r and r dash. Let r and r dash be the radii of convergence of the series, convergence of the power series. Let summation n run from 0 to infinity an z power n and summation n run from 0 to infinity an z power n minus 1 respectively. Then we say limit n tends to infinity, absolute values of an whole power n minus n 1 by n, absolute values of an whole power 1 by n should be equal to 1 by r, and limit n tends to infinity, absolute values of n into an whole power 1 by n should be equal to 1 by r dash. To show that r is equal to r dash. So our aim to show that limit n tends to infinity n into 1 by n. So limit n tends to n into whole to the power of 1 by n. So is equal to 1. So limit n tends to infinity, n power 1 by n should be a 1. So first to show that limit n tends to infinity, n to the power of 1 by n is 1. by Cauchy condition, by Cauchy theorem on limit, if we take this, limit n tends to infinity, a n to the power of 1 by n should be equal to limit n tends to infinity, a n plus 1 divided by a n. So, our aim should be equal to limit n tends to infinity, n to the power of 1 by n is equal to limit n tends to infinity, n plus 1 divided by n. So, if we take n as a common, n of 1 by 1 plus 1 by n divided by n. So, n get cancelled. The limit n tends to infinity, we get 1. So, this is a finite quantity. This is a finite. We can come to the one more theorem here. The analytical way of saying, see, one way is conversions either to show that r equal to r is equal to r1. So we saw. Now we come to this function is analytical. In the sum of the power series, the sum of the function f of z of a power series summation a n z power n represent an analytic function inside the circle of a convergence. Inside the circle of a convergence. The same statement it says in another way. The same statement it says another way. If the radius of a convergence of a power series, if the radius of the convergence of a power series summation a n z power n is a positive real number, or then the power, then to prove that the function f of z defined f of z equal to summation a n z power n is analytic mod z less than r, is analytic mod z less than r. So here one function we say is the powers function, we say a n z power n is k one function, we call that one function. Derivative of this function we call this another form. Say I call this f of z equal to the power series summation n run from 0 to infinity a n z power n. The derivative function I call that function g of z equal to summation n run from 0 to infinity n a n z power n minus 1. So let r be the radius of the convergence of the power series summation a n z power n. Then r dash is also radius of a convergence of the power series n a n z power n minus 1. So r is the convergence of the power series f of z. R dash is the convergence of the power series g of z. So which is the derived the series of summation a n z power n. Let z be any point within the circle mod z equal to r. So that z be any point on this within the circle mod z equal to r, so that mod z less than r also there exists a real number there exists a real number or positive such that mod z less than r. So if we choose any real number here, this real number lies between mod z and we are choosing the convergence of a number r, that is capital R. Mod z less than r less than r. Then the series of the power series summation a n z n convergence for mod z less than r, so that the power series bounded. Simply say this power series is bounded. So if you bounded, suddenly this number is bounded some number. We call that number should be a capital M. Suddenly there exists a finite real number, say m greater than 0, such that the power series mod a n z power n less than m. So for the sake of a convenience, we write mod z equal to rho and mod h equal to epsilon. We call this sake of convenience. So that is mod z plus mod h less than r. So this is called mod r. H is also chosen that. So we come to the definition form in the analytic form, means derivative condition form. Mod f of z plus h minus f of z divided by h minus g of z. So this equal to absolute values of summation a n of z plus h whole power n minus z power n divided by h minus n z n minus 1. So again I am simplifying. Suddenly this number is less than or equal to summation n run from 0 to infinity absolute values of a n into into rho plus epsilon whole power n minus rho n divided by epsilon minus n epsilon to the power of n minus 1. Again, I am simplifying this. Suddenly, this number is less than summation n run from 0 to infinity m. This number is suddenly is bounded. This is the number is bounded. That bound number should be a capital M. M divided by epsilon into r power n of rho plus epsilon to the power of n minus rho to the power of n minus n epsilon rho to the power of n minus 1. So I am taking LCM. Here I am taking LCM. That number you take outside. So we take that. So this number suddenly epsilon 1 is bounded. That number we call this is positive number m. Suddenly m divided by epsilon to the power of r of n of rho plus epsilon to the power of n minus rho to the power of n minus n epsilon rho to the power of n minus 1. Suddenly this number we can express this formula form, that is suddenly this number is bounded. I say this number is bounded. You say m divided by epsilon. This will be m divided by epsilon of 1 divided by 1 minus I take common 1 minus of rho plus epsilon divided by r minus 1 by 1 minus rho by r minus epsilon by rho of summation n run from r run from 0 to infinity n of rho by r whole to the power of n. I call this equation 1. M divided by epsilon of 1 divided by 1 minus rho plus epsilon by r minus 1 divided by 1 minus rho by r minus epsilon by rho into summation r1 from 0 to infinity n times of rho by r whole power n. I call this equation 1. Suddenly this number of 1 by 1 minus epsilon plus rho plus epsilon by r is equal to r divided by r minus rho minus epsilon. I call this. Let this number we call that number a. I call denoted by a, means let a should be equal to summation n run from 0 to infinity n times of rho by r power n. I call that should be a capital A, means a is equal to capital A is equal to summation r run from 0 to infinity n times of rho by r whole power n. Then we write simplified this equal a equal to rho by r plus 2 times of rho by r whole square plus 3 times of rho by r whole cube, etc. This is power series expansions. So simplify this again. So rho by r a is equal to p by r whole square plus 2 times of rho by r cube, etc. Substituting or subtracting 1 and 2, we get here only a time. So I take a as a common 1 minus rho minus r. 1 minus rho by r, simply say. So a as I take means a minus rho by r times of a. So I take a as a common, we get 1 minus rho by r. So this is equal to rho by r plus rho by r whole square plus rho by r whole cube, etc. etc. Suddenly this can be written as rho by r divided by 1 minus rho by r. Again, a should be equal to rho by r divided by 1 minus rho by r whole square. So again we are simplifying r rho divided by r minus rho whole square. So again we write then you come to the equation 1 form. So again I am substituting, I come to the 1 form equation. Mod absolute values of f of z plus h minus f of z divided by h minus g of z. This implies less than m by epsilon of r divided by r minus rho minus epsilon minus r by r minus rho minus epsilon r divided by r minus rho whole square. This number is equal to mr divided by epsilon times of 1 minus r minus rho minus epsilon minus r minus rho plus epsilon divided by r minus rho whole square. So this suddenly this is number m times of this suddenly is bounded form. This can be written as mr epsilon square divided by epsilon r minus rho minus epsilon r minus rho whole square. This number say absolute values of f of z plus h minus f of z divided by h minus g of z is less than epsilon mr divided by r minus rho whole square of r minus rho minus epsilon. Make h tends to 0 so that absolute values of h equal to epsilon. This also tends to 0. We get, so limit h tends to 0, absolute values of f of z plus h minus f of z by h minus z of z less than or equal to 0. That is, say limit h tends to 0, f of z plus h minus f of z divided by h should be equal to g of z. This is the modulus of quantity is always greater than or equal to 0. That is, say there is a derivative. So this is the left hand side is a derivative of f of z. Say derivative of f of z should be equal to z of z. Derivative of f of z should be equal to z of z. But g of z exists, so that derivative of z is exists for all values of z, such that mod z less than r. Such that mod z less than r. It means that f of z is analytic for mod z less than r, f of z is analytic mod z less than r, and g of z is a derivative. Is f of z is analytic, g of z is derivative. So again you come to the g of z is again a power series with the same radius of convergence. We can differentiate this power series in order to obtain the second derivative of original series. This is the main second derivative of original series. A proof can be written on the same lines to prove that the second derivative is also analytic inside the same circle mod z equal to r. Inside the same circle mod z equal to r. Moreover, the derivative can be found by term differentiation. The sum functions of power series represent an analytic function inside the circle of convergence. This is the way where one function is convergence, the other function is derivative function, the same way is convergence in the same form. So this is the way I can prove. The working rule, the same way we take a problem in the next slide. 1 by r, we call this limit n tends to infinity, an all power 1 by n should be equal to limit n tends to infinity, a n plus 1 divided by a n. So this is the working rule to convergence of the radius of a convergence.